Okay, let's continue with multiplication. Let's begin. Can we multiply integers? So we first consider, can we multiply natural numbers? So yes, we can. For example, we can multiply apples. Three times 7 apples equals 7 apples taken thrice, added thrice, equals 21 apples. So 3 times 7 apples is 21 apples. So another example of multiplication. Same example, 3 times 7 is 7 plus 7 plus 7, which is equal to 21. So to do 3 times 7, you add 7 3 times, get to 14, get to 21. 3 times 7 means adding 7 3 times. Okay, so this is how we multiply natural numbers. We can ask, does order matter in multiplying natural numbers? So the observation is, like with addition, we have commutativity. For any natural numbers, a times b is b times a. For example, 3 times 5 apples is equal to 5 times 3 apples. So 3 times 5 apples is this. You're taking 5 apples 3 times. You can also take 3 apples 5 times. Five 3 times 5 apples is 5 times 3 apples, which is both are equal to 15 apples. So a times b is b times a. This is one example. Okay. Now we can ask, does grouping matter? In multiplying natural numbers? So the observation is it doesn't matter for any natural numbers a, b, c. A times bc is ab times ab times c. Okay. And another observation, which is multiplication by 1 and 0 for any natural number a. We have the basic observation 1 times a is a, and if you take a 0 times you get 0. Okay, so these are some basic observations. Order doesn't matter in multiplying natural numbers, grouping doesn't matter in multiplying natural numbers. And now we can ask, how does the multiplication operation interact with the addition of two natural numbers? So the observation is distributivity of multiplication over addition. So for any natural numbers a, b, c, we in fact have a times b plus c is a times b plus a times c. So we can illustrate this by an example. Three times 2 apples plus 5 apples equals 3 times 7 apples equals 21 apples. And 3 times 2 apples plus 3 times 5 apples equals 6 apples plus 15 apples equals 21 apples. So both are equal. Oh, why is this the case? Let's see. We saw these, they are equal, but more intuitive explanation would be 3 times 2 apples. So let's take 2 apples fully plus 5 apples. So 3 times 2 apples plus 5 apples equals, so we are taking this 3 times. So this is 3 times 2 apples plus 5 apples, and we can group these together and group these together. So we get 3 times 2 apples plus 3 times 5 apples. So we saw that 3 times 2 apples plus 5 apples is, or let's write it fully, 3 times, so we saw this, why this is true. So 3 times 2 apples plus 5 apples, we are expanding it like this, 3 times 2 apples plus 5 apples written fully, and we are taking three of these terms and grouping like this. We are getting 3 times 2 apples plus 3 times 5 apples. So 3 times 2 apples plus 5 apples is 3 times 2 apples plus 3 times 5 apples. Okay, so this is how we sort of show that multiplication distributes our addition. A times b plus c is a times b plus a times c. Okay, so these are the basic properties of multiplication. Order doesn't matter, grouping doesn't matter, and multiplication distributes our addition. So this is for multiplication of natural numbers. Now we still have our original question, can we multiply integers? We haven't answered that yet. Can we multiply integers? Okay, so suppose we define multiplication of integers. We want it to satisfy so we want this property. So multiplication with natural numbers, so for any natural numbers, so all these properties are for natural numbers. We haven't shown these properties for arbitrary integers. So we are asking, can we multiply integers? Suppose we define multiplication of integers. We want it to satisfy the same properties, like for any integers a, b, c, we want order to not matter, that is ab equals ba, and we want distributivity. A times b plus c is a times b plus a times c. We want these two properties. Now multiplication of a natural number by a natural number, we already saw this is clear. For example, we can take the same example, 3 times 7 is, so take 7 3 times, meaning add 7 to itself 3 times, you'll get 21. So multiplication of a natural number by a natural number is clear. Also multiplication of a negative number by a natural number is clear. For example, 3 times minus 7. So when multiplying this negative number minus 7 by 3, you do the same thing. Add minus 7 to itself 3 times and we will get minus 21. So multiplication of a natural number by a natural number is clear. Multiplication of a negative number by a natural number is clear. Now the question is to define multiplication for all integers. How can we multiply. So have I underlined? Yeah. How can we multiply a negative number by a negative number? For example, what is minus 3 times minus 7? So by the way, we want this. We want any integers, for any integers a, b, c, we want commutativity to hold and distributivity to hold. So as suppose we define multiplication of integers, we want it to satisfy this. So we can write, if at all there is an ideal multiplication like the one we wanted, if at all there is an ideal multiplication of integers it must satisfy a times b plus c equals a times b plus a times c. Hence, so it must satisfy. So we are interested in finding minus 3 times minus 7 as an example. What is minus 3 times minus 7 in this ideal multiplication scenario? So let's see. It must satisfy minus 3 times 7 plus minus 7 equals, it should distribute minus 3 times 7 plus minus 3 times minus 7. Hence, minus 3 times 0 equals minus 3 times 7 plus minus 3 times minus 7. Hence, 0 equals minus 3 times 7 plus minus 3 times minus 7. So multiplication by 0 equals so minus 3 times 7 is 7 times minus 3 because we want commutativity, and 7 times minus 3 is adding minus 3 to itself 7 times, which is minus 21, right? Okay, let me write it again. Or I'll write it here itself. So this is in an ideal scenario, this is 7 times minus 3, which is minus 21. So hence 0 equals minus 21 plus minus 3 times minus 7. So adding 21 both sides, minus 3 times minus 7 is, we found 21 in this ideal scenario. So if at all there is an ideal multiplication of integers, in that ideal multiplication we have minus 3 times minus 7 is 21. Okay, this suggests that we define. So we saw that multiplication of a natural number by a natural number is defined. Multiplication of a negative number by a natural number is defined. If we sort of impose commutativity and distributivity, we get we sort of can reduce multiplication of two negative numbers as well. using the distributivity and commutativity rules and the usual multiplication rules for natural number times any integer. Okay, so this suggests that we define definition. So this is for negative times negative. Okay, I'll recap once again. So multiplication by natural numbers is very clear. Multiplying a natural number by a natural number is clear. Multiplying a natural number by an arbitrary integer is clear. And so to multiply two negative numbers, we define for any natural numbers a, b, we define minus a times minus b to be is the definition ab. So what suggests this definition? The above computation suggests this definition. Suppose we have an ideal multiplication defined for all integers, then it must satisfy commutativity and distributivity. Hence it must, so using those rules, we found for one specific example, minus 3 times minus 7 is 21. We are getting in that ideal scenario, minus 3 times minus 7 is 21. This suggests that we have not defined how two negative numbers can be multiplied. We have defined all other kinds of multiplication, positive times negative, positive times positive, etc. So to define two negative times negative, we define this as minus a times minus b is ab. We hope with this we have defined multiplication of any two integers. So now that we have defined multiplication of any two integers, we can ask, is this multiplication an ideal multiplication? Do we have commutativity and distributivity? So the properties for multiplication of the key properties for multiplication of two natural numbers is that they are commutative and we have distributivity as well. These are the key properties. So we are asking, now that we have defined the multiplication of any two integers, is this multiplication an ideal multiplication like the one we want? Do we have commutativity and distributivity? It turns out yes. Observation, commutativity. So now we can make statements for any integers. For any integers a, b, we have a times b is b times a. Previously we made the commutativity statement for multiplication of two natural numbers. Now we are making for arbitrary integers, distributivity of multiplication over addition for any integers a, b, c. A times b plus c is a times b plus a times c. So we do not prove it here, but we can take examples. So we'll take one example. -2 times 3 plus -6. So this is -2 times -3, which is +6. By the way, we define multiplication of two negative numbers. -a times -b is ab for any natural numbers ab. Okay, now we can also study the distributed version, and -2 times 3 plus -2 times -6 equals -6 plus 12 equals 6. And we see that both are equal. So this is an example showing that a times b plus c is a times b plus a times c for all integers a, b, c. Okay. So the above definition of multiplication of two integers is indeed an ideal multiplication. It satisfies distributivity over addition. Okay. Now we have defined multiplication of any two integers, and we have looked at some basic properties of multiplication. We can ask, how does multiplication by -1 affect integers? So the observation is, for any integer a, -1 times a is the additive inverse minus a. Okay, so here is a proof. A plus, let's consider a plus -1 times a. This is 1 plus -1 times a equals 0 times a, which is equal to 0. Hence a plus box equals 0 for box equals -1 times a. Hence, by definition of minus a equals, or we can write -1 times a equals, hence -1 times a is the additive inverse of a. Okay, now we can ask, can we generalize this? So the generalized observation is, for any integers a, b, minus a times b is minus of a times b. So for a equals -1, one second. For a equals 1, we get the, for a equals 1, we get the above result. Or you can say, putting a equals 1, we get the above result. That -1 times b is minus of b. Okay, so proof is the same. Same as with -1 times a equals minus a proof. So we consider ab and we add this quantity -a times b to it. We get a plus minus a times b, which is 0 times b, which is 0. Hence ab plus box is 0 for when box is minus a times b. Hence minus hence minus a times b is actually the additive inverse of the product AB. Right, so it's the same proof. And we can consider an example. Let A, B, C be integers. Then minus 2a times 3b times 4c. Consider a product like this. So first, minus of a is minus 1 times a, right? So we can take minus 1 outside of the first term and we have this product. And so we have minus 1 times 24abc, and again we can take the minus 1 inside. Minus 1 times an integer is minus of that integer, so this is minus 24abc. We have simplified this product. Minus 2a times 3b times 4c. The additive inverse of 2a times 3b times 4c is the additive inverse of 24abc. Right. That's all for this part. See you in the next part.